Good afternoon. Can you all hear me?
Yes.
Hello, can you hear me?
Yes.
Okay. I want to cover two different topics, unrelated. The first one is lazy evaluation. The fundamental issue here has to do with Boolean expressions. So let's look at a Boolean variable b, and it consists of testing two function evaluations. We have f of x is greater than 0, or f of y is less than 0. Now, typically we tend to view Boolean expressions very similar to arithmetic expressions. So if I had an arithmetic expression, z is f of x times f of y, well, in this case, in the case of an arithmetic expression, I would imagine that all of you would be fully expecting that
Hey, Professor.
there is a function evaluation of f for x, and there's a function evaluation for y, and then the product of those values
I'm sorry, Professor.
is formed and is assigned to z. And so, in particular,
I don't think he
if
hears
your
us.
function f has some kind of side effects, for example, it might involve printing out a couple of lines of output, say 2 lines of output for each function call, then clearly when you determine the value of z, you would expect 4 lines of output to be produced. 2 for the call of x with call of f with x as parameter, and 2 for the call of f with y as parameter. Now, you probably will have a similar question for the Boolean expression. So you tend to think that perhaps you get two lines of output for f of x and 2 lines of output for f of y, and so evaluating the Boolean expression b would then result in 4 lines of output. And it may not be that way. You may only get 2 lines of output. So how can that be? Well, the reason why this is lazy evaluation. Lazy evaluation has some rather serious implications. issue here is that a compiler that is interested in efficiency may make the following observation. This is a Boolean expression, B. And so if I am interested in determining the value of that Boolean expression B, if f of x is indeed greater than 0, then this will evaluate to a true. And B, therefore, is guaranteed to be true just on the basis of the fact that f of x is greater than 0. In other words, the evaluation of f of y and testing whether that is less than 0 is entirely immaterial. B will be true if f of x is greater than 0, regardless of whatever happens with f of y, and therefore a compiler that tries to be efficient will perhaps forego altogether the evaluation of f of y. And so what that really then means is that there is no you're not seeing my PowerPoint? I have nobody muted. But I have nobody muted. I don't know what. Do you see that PowerPoint now?
No, we do not.
Yeah, well, I don't hear anything. I see the little notice nobody sent. Okay, do you see it now?
Yes, we can see it.
Okay. Do you see it now?
Yes, sir.
I guess you do. But I can't hear anything you're saying. Don't know what the deal is. So lazy evaluation basically consists of observing that for a Boolean function, for a Boolean expression, the first portion, f of x greater than 0, if that is true, there's absolutely no point in doing the second evaluation, f of y, because even if it were true, it's not going to change the values of b. It is already determined to be true on the basis of f of x being greater than 0. So the only time f of y would have to be evaluated is if f of x is not greater than 0. At that point, the first portion would be false, and then the value of the Boolean expression b would be exactly the value of the f of y less than 0. So if your compiler does that kind of thing, then I don't have to, I cannot necessarily expect that in this case you might get 4 lines of output, because it may do the first half of the expression, determine that f of x is greater than 0, and then conclude that b is true without consulting the next portion, the f of y. Now, this is not entirely different from an arithmetic expression. If you look at the z gets assigned f of x times f of y. It is conceivable, although it is not particularly useful, it is conceivable that evaluating f of x and determining that f of x in the value of z, f of x is 0, then of course there's no point in looking at f of y because we know that z is 0. The reason why this is not typically done in any compilers that I'm aware of is that the likelihood that f of x is 0 is very low. Now, if you look at the Boolean expression, b, under certain reasonable probability distributions, f of x is greater than 0 with probability 50%. So half of the time, there is no need to look at the f of y. And so, if the evaluation of the function f is expensive, then obviously we're gaining a great deal of efficiency by doing only half of that. In the case of the arithmetic expression z, well, the likelihood that f of x is 0 is relatively low. It's probably not 0, but it is relatively low, and therefore that is not particularly interesting and therefore not particularly profitable to evaluate in a lazy form. Then in this case the arithmetic expression obviously is f of x times f of y, and you will get both evaluations. In the Boolean expression, however, it is very common that a good compiler will do lazy evaluation. Now, if that bothers you, you can, of course, force the compiler to do things the way you want it done. You do b1 is f of x greater than 0. b2 is f of y less than 0, and then b is b1 or b2. In this case, even if your compiler were to do lazy evaluation, it would not be able to do that because you're basically requiring the compiler to compute b1 and then compute b2, and then b1 or b2 is going to be the value of b. Now, this is important from a programming point of view because of the following scenario. You may have a program written in a high-level language that you have been led to believe is portable. Well, it isn't, because if you take that program and you compile it with a compiler that uses lazy evaluation, then you get one result. If you're compiling it with a compiler that does not do lazy evaluation, you may get a different result. Generally, programming languages do not specify explicitly whether or not lazy evaluation must be used. So what that means then effectively is that you really don't know what is going to happen. You really don't know whether lazy evaluation is going to be applied or not. And as a result, that mythical portability of your high-level language program really isn't true at all, because different compilers for the same programming language may give you different results. So that's important from a programming point of view, because you may get the situation that I just described, and in most cases both compilers will in fact be standard compilers. Because if the programming language does not specify what should be used, a compiler writer can decide on his or her own whether lazy evaluation is going to be used or not. And if one compiler writer says yes, lazy evaluation, the other compiler writer says no, no lazy evaluation, then you have two compilers. Both of them are standard, both of them are for that programming language, and yet your programs will behave differently when executed. So that is a rather important issue, because you can't really rely on that. And for the most part, I suspect that you do not know whether your favorite programming language uses lazy evaluation or not. So it is an important issue here to actually be aware what is happening, and if your program behavior depends crucially on the evaluation of everything that is involved in this particular Boolean expression, then you probably will have to go with that somewhat kludgy way of breaking it up into two different Boolean expressions and then composing the ultimate Boolean expression B in terms of the two parts. And so that, of course, is somewhat problematic, because you don't really have a good way of determining what is happening unless you're actually alerted to that. And so that's the purpose of pointing this out, that you really should be aware that there could be hidden landmines, because as I said, most programming languages don't specify explicitly what has to be done, and so that leaves the compiler writer free to decide. And if one says lazy evaluation and the other one doesn't, you now end up with two different compilers, both of which are standard, both of which implement the language, but yet the execution of a program with these two compilers will provide you with two different outputs. And that is unusual and certainly unexpected for most people, because you have been led to believe that these programming languages, the standard ones that you use, are all quite portable, and that's of course not really true. Any questions? Okay, so then I will go to another topic, the second topic that we're going to do today, and that is matrix multiplication. So we have three n by n matrices, A, B, C. They're n by n matrices, and we want to do C is A times B. Now, the standard algorithm that we've already beaten to death is, of course, the three nested loops, I from 1 to n, j from 1 to n, using row matrix Cij is 0, and then k from 1 to n, Cij plus aik times bkj. That's the standard algorithm that you all know, that we've already abused extensively before, and so that, of course, is order of n to the third. 3 nested loops, every one from 1 to n, so that obviously gives you order of n to the third, and that is what you all probably think of when we talk about matrix multiplication. Well, we can, in fact, do this a little differently. As you know, we are frequently interested in formulating things recursively, and so let's look at what is happening here. We have a matrix A and a matrix B and a matrix C, and what we can do is we can basically cut these matrices into quarters. And so if this is A11 and A12 and A21 and A22, then this is B11 and B12 and B21 and B22 and C11 and C12 and C21 and C22. And now what we can do is this multiplication. We can write this in terms of those quarter matrices. And so C11 is then A11 times B11. So this times that, plus A12 times B21. So this times that. So it's this row with that column, and so this is the same story as before. And so we have C11 is A11 times B11 plus A12 times B21. And similarly C12 is this row with that column. So we have A11 times B12 plus A12 times B22. And then C21 is this row with that column. So A21 times B11 plus A22 times B21. This row of A with that column of B. And finally, the last C22 is equal to this row from A with that column from B, A21 times B12 plus A22 times B22. And now if we look at this, then we basically have a recursive algorithm here, because we've replaced the original problem of computing the product of A and B, which are n by n matrices, to the problem of computing the product of portions of these matrices, quarters specifically. A11, A12, A21, A22, B11, B12, B21, B22, and corresponding C11, C12, C21, and C22. And so if we look at this from the computational complexity point of view, we can clearly again invoke as usual, our master theorem for recursive functions, because we're basically replacing this problem of multiplying A and B with a number of subproblems. And so the standard question that we have to ask in this context is, of course, as usual, what is C and what is R? C is, of course, going from N to N divided by C. And R is how many recursive function calls we need in order to carry out the operation that we want to carry out. So what is C in this case? Nobody?
Can you state the question one more time,
What
Professor?
would C be? Well, we're going from an n by n matrix, A, B, and C, these are n by n matrices, to n over 2 by n over 2 matrices, C1, C11, C12, C21, C22, and same thing for the A's and the B's, the quarter matrices. So we're going from n to n over 2. So C is then clearly 2. And so what is R? Nobody? No, not n over 2. What is R? How many recursive calls do we have to replace that one multiplication, A times B?
2.
Well, you just have to count. We have A1 1 times B1 1. We have A1 2 times B2 1. We have A1 1 times B1 2, A1 2 times B2 2, etc. So what is R?
8. 8.
8, exactly. R is 8. Because we have 1, 2, 3, 4, 5, 6, 7, 8 multiplications of matrices that are now not n by n, but n over 2 by n over 2. And so our master theorem then says the complexity of that is n to the power of log base c, which is 2, of r, which is 8, which is order of n to the third. So all this for nothing, because basically we haven't gained anything. This is still only n to the third, which is of course exactly what we had for the three nested loops, and so that didn't buy us much apparently. Well, not quite. Here is what we're going to do now. We are still assuming we have these quarter matrices, and now instead of doing this with C11, C12, C21, C22 given that way, we're going to do the following. And now you have to bear with me. This is another one of those Rube Goldberg constructions, and we have S1 is A21 plus A22. If you don't want to write this down, copy it down, this is on page 56 in the book, so there's not much point in actually copying it down, but I will do it simply because we have to have this so we can discuss it. So we have S1 is A21 plus A22, and S2 is S1 minus A11. S3 is A11 minus A21. S4 is A12 minus S2. Then we have S5 is B12 minus B11. S6 is B22 minus S5. S7 is B22 minus B12. And S8 is S6 minus B21. Then we have M1 is S2 times S6. We have M2 is A11 times B11. We have M3 is A12 times B21. M4 is S3 times S7. M5 is S1 times S5. M6 is S4 times B22, and M7 is A22 times S8. Then we have T1 is M1 plus M2, and T2 is T1 plus M4. And now comes the crucial claim. C11 is M2 plus M3. C12 is T1 plus M5 plus M6. C21 is T2 minus M7. And finally, C22 is T2 plus M5. Now, we still have to verify that this is indeed correct, but let's for the moment assume that this is indeed true. So what do we get? What do we get when we look at this? Well, this is of course a recursive formulation, just like this one was. Here we replace C is A times B by those 8 multiplications. And so the question is, what did we do here? How many multiplications do we need to carry out in order to get this? And as I said, we still have to verify that claim, which I will do in a few minutes. But now first let's justify why are we going to do that. So obviously all of these operations involve those quarter matrices, n over 2 by n over 2 matrices, A's and B's. And so the C's then are given by those expressions. And so the question then is, what is the complexity of this algorithm, which seems to be another Rube Goldberg contraption? But if we did carry out the actual analysis, well, once again, we have two questions. The only two questions whenever we deal with recursive function, and that is, what is our C? Well, nothing has changed. The C is obviously 2 as before. We go from n to n over 2 for the matrices. These are n by the original matrix. Original matrices A, B, C were n by n matrices, and now we're replacing them by n over 2 by n over 2 matrices. So the C obviously is still the same, 2. But the question is, what is R? How many multiplications do we actually have? Nobody? Yep, 7. We have 7. We have 1, 2, 3, 4, 5, 6, 7. So R is 7, which of course is a very different story from what we had before, where R was 8. So what does that mean? The complexity of the algorithm then is n to the power of log base 2, which is C, of R, which is 7, which is approximately n to the power of 281. Now you may say, well, big deal, 281 versus 3. Well, but this is an exponent. If your n is 1,000 or 10,000, then there is a great deal of difference between 10,000 raised to the power of 2.81 versus 10,000 raised to the power of 3. Basically, you're talking about 2 orders of magnitude. Now, of course, it is kind of weird because this looks so much more complicated. Okay? So, compared with simplicity itself, we had basically 8 multiplications and 1, 2, 3, 4 additions. If we compare that with the method that I've just written down, well, we have 1 addition, 2, which is a subtraction, but it doesn't make any difference, so we'll lump them all together. 1 addition, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 additions as opposed to 4. But of course, this has 8 multiplications and this has 7. Now, the crucial observation here is that a multiplication is an expensive operation. We'll have to talk a little bit more how expensive, but it is an expensive operation. On the other hand, an addition is cheap. It's n squared. Multiplication obviously is more expensive than n squared. If few comments in a minute about that, but for the time being, it should be fairly obvious that nothing we can multiplication is certainly not going to be n squared. It's a lot more involved. And so what we have basically done is traded 11 additions for one multiplication, because we have now 15 additions and 7 multiplications versus the 4 addition and 8 multiplication. And so effectively what we can do is we can sort of ignore the fact that we have more cheap operations, because we can save ourselves one expensive one. And so that is what this whole process is all about. And so this is a complexity that is significantly better than the complexity of the standard algorithms, which is this one of the 3 nested loops. And in fact, this algorithm, which is due to a person, German mathematician by the name of Victor Strassen, about 40 years ago, is eminently practical. If n is greater than 50. So obviously, if you have a 3 by 3 matrix, you don't want to do Strassen's algorithm. But if you have a 1000 by 1000 matrix, you're certainly going to be much, much better off with that algorithm than with the standard 3 nested loops that one typically deals with. So the issue here is, and before I actually verify that, a few comments about the question, what is an optimal matrix multiplication algorithm? The short and the long is we have no idea. We have no idea what is optimal. We do know that the 3 nested loops is definitely not optimal. We know that because Strassen's algorithm is beta. It turns out that actually we also know that Strassen's algorithm isn't the best. There are better algorithms, algorithms that asymptotically are faster than Strassen's algorithm. The only problem with those, and of course what happened was that for many years, in fact centuries, everybody thought that essentially those 3 nested loops was the way to do matrix multiplication, and there was no good reason to do it any other way, because that was it. So when Strassen then came up with that algorithm, that basically opened the floodgates, because now people started thinking, well, obviously the 3 nested loops weren't the best way to do it, so here is a method to improve. But then people started looking at, well, can we do better than Strassen? And the answer was yes. So every 10 years or so, a better algorithm came up, improving over whatever was best known at that point. The only problem with these subsequent algorithms is that they're really not terribly practical. You may have algorithms for matrix multiplication that are better than Strassen's algorithm, but they will only be useful, practically speaking, if your n is maybe 300,000. So this is a 300,000 by 300,000 matrix. And obviously, for all practical purposes, that's not going to be of particularly practical interest. So we know that Strassen's algorithm is definitely not optimal because we have better, asymptotically better algorithms. But from a practical point of view, at this point, the algorithm that really should be used if you have large matrices, say 1,000 by 1,000, 100,000 by 100,000, anything in fact where n is greater than 50, you should start with Strassen's algorithm and then use as basis element when n is less than 50, less than or equal to 50, you use the three nested loops. So what is important is that anybody who uses the three nested loops for large matrices is crazy. Shouldn't be used, really should be used. Strassen's algorithm should be used until the sub-matrices that occur in that process become small in this case, in less than or equal to 50. So what is, of course, important here is that we don't really know what is optimal. We know that Strassen's algorithm is not optimal. We don't know any non-trivial lower bound. We know an obvious trivial lower bound, which is n squared. N squared is the number of elements in C, so obviously, since we have to define n squared numbers, we have to have an algorithm that at least takes order of n squared time. Can it be done in n squared? Well, we don't know. Nobody believes that it can be done in n squared. That's sort of a pipe dream, but we don't really have any proof. We don't know of any better lower bound. And so that means that if somebody were to come up with an algorithm and claim that this algorithm does matrix multiplication, it does it in time n squared, order of n squared, one would actually have to look at the algorithm and the analysis. Nobody would believe it, but it can't be dismissed out of hand. If, on the other hand, if you recall, we've proven a lower bound on sorting by comparisons for n numbers, well, if somebody, as I have mentioned already several times, if somebody claimed to have come up with an algorithm that sorts n numbers by comparisons and does it in linear time, nobody has to look at that. That algorithm is clearly not going to work, at least not in the time complexity that the person claims. So in this particular case, we know it can't be true, and therefore we don't have to look at it. If somebody were to come up with a matrix multiplication algorithm and claims that this runs in n squared time, at a minimum one would have to look at it. I mean, one would probably look at it with very jaundiced eyes because nobody believes that this will ever happen. But one couldn't just shoot it down by saying, well, this obviously can't be true, like in the case of a sorting algorithm that runs in linear time in the number of elements. So that is basically the fundamental problem that Strassen created for us, because now nothing is known. We have no idea what is a good matrix multiplication algorithm. We know that Strassen's algorithm does it in time that is significantly less than the three nested loops, but at the same time, it's been established that Strassen's algorithm isn't optimal. And so before he came up with his algorithm, everybody was perfectly happy with the three nested loops. Now, of course, that's no longer true, and nobody really knows where it will all end up. And certainly the one thing that we do know is that virtually nothing that we can practically use is optimal. So this complexity is useful, it is practical. Strassen's algorithm is, as I said, if n is greater than 50, it should be applied. And so the only thing that's left to verify is that this is actually true. I mean, that's obviously something we'll have to verify. So, C11. Well, what are we going to aim for? Well, we're going to aim for those expressions. So C11, we've already said, is A11 times B11 plus A12 times B21. Well, in this particular case, that's trivially true because M2 is A11 times B11, and M3 is A12 times B21, and so this C11 is exactly that. So that was a trivial exercise. Then let's pick the next one, C12. So we have T1 plus M5 plus M6. So T1 is M1 plus M2. This is now a good deal of busy work. Okay? And then M1 is S2 times S6. And M2 is A11 times B11. And M5 is S1 times S5. And M6 is S4 times B22. Now S2 is S1 minus A11. So S2 is S1 minus A11, and A1 is A21 plus A22 minus A11. So this is S2 times S6. S6 is B22 minus S5, which is B12 minus B2 minus B11. So since we're subtracting S5, so we have minus B12 plus B11. So this is S2 times S6, then we have A11 times B11, and then we have S1 plus S5 times S5, so this is A21 plus A22, so this is S1 times S5 is B12 minus B11, so this is S5, and then we have S4. S4 is A12 minus S2. S2 is S1 minus A11, so this is plus A11, because we have a minus S2, and the S2 is S1 minus A11, and then we have S1 is A21 plus A22, so we have minus A21 minus A22. So this is the S4 times B22. And so the way in which we're going to do that is, if you look at this, then you will see that all of these, we have to do this, and we have to do that, we have to do this, and we have to do that. And so in all of these, what you see here is that the left of it, on the left of the multiplication, there are only A's, and on the right of the multiplication, there are only B's. So we're going to create a little table where we have the B's here and the A's here. So we have a B11, B12, B21, and B22. And we have the same thing for the A's, A11, A12, A21, and A22. And so let's start with this A21. So this is the A21, the A22, and the A11. So it's the first, the third, and the fourth. And then we have to deal with the B's. So the B22 is the B22 column. So we have A21, and so this is positive, so I put a plus here. A21, B22 times B22. Then A22 times B22, this is a plus. And then A11 times B22, but this is with minus A11, so I get a minus here. Then I have the same thing with B12, which is that column, B12, but with a minus. So I have minus A21, minus A22, plus A11. And then I have the same thing for the B11 column. So this is A21 with a plus, A22 with a plus, and minus A11. So these are those. Got those. Then we have to do the A11, B11. That's a plus. So I got that. Then I have to do the A21 and the A22, A21 and A22. So these are these two rows with B12 and B11. So A21 and A22 with B12. This is a plus and this is a plus. And then I have B11, but with a minus, because this is minus B11, so I have a minus and a minus here. And so I got those. And finally, I have this last term, A21, I'm sorry, A12, A21, A22, and A11 for the B22 column. So A12 is a plus, A21 is a minus, A22 is a minus, and A11 is a plus. And so if you look at this, then you will see that the plus and minus cancel here, 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 cancel here. So the only thing that's left is A11 times B12 and A12 times B22. And if you look at this, then that is exactly A11 times B12 plus A12 times B22. So this is the C12. So we've verified that. Everybody clear on how we're doing that? And now let's do the C12. I'm going to erase all that and You have to watch me before I screwed this up completely. So let's see whether I get it right this time or whether I'm going to screw it up again. So get rid of these. Okay, so we have the table empty, and so we are going to do the C12, and that is T2 minus M7. And T2 is T1 plus M4, and T1 is M1 plus M2, so we have M1 plus M2 plus M4 minus M7. So M1 is S2 times S6. M2 is A11 times B11. And M4 is S3 times S7. And finally, M7 is minus A22 times S8. Okay, so S2 is S1 minus A11. So S2 is A21 plus A22 minus A11. So that's S2 times S6 is B22 minus S5 is B12 plus B11. So this is that. Then we have that, and then we need the S3, which is A11 minus A21 times S7 is B22 minus B12. And finally, we need the A minus A22 times S8, and the S8 is S6 minus B21. So S6 is B22 come on. So we have S6, S8 is S6, and S6 is B22 minus S5, which is B12 plus B11 minus B21. So that's that. So we have this, and we have that, and we have this, and we have that. So let's start with this. This is the A21 row, the A22 row, and the minus A11 row. So this is B22. We have a plus here, and a plus here, and a minus here. Then we have the B12. So a plus here, and a minus here, and a minus here, because plus and minus is a minus, A22 minus B12 is a minus, and minus A11 minus B12 is a plus. And then we have A21 with B11, so this is a plus, this is a plus, and this is a minus. So we got those 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 3 times 3. Then we have the A11 times B11. This is a plus. So we got that one. Then we do this, A11 minus A21, A11, A21 with B22. So A11, B22 with a plus, and B12 with a minus, and then A21, B22 with a minus and a plus. Minus is plus. And finally we have A22 with B22, with B12, with B11 and B21, but all with a minus, because this is minus M7, which is minus A22 times S8. And so this is minus A22 times B22, so this is a minus, and minus 1, 2, so this is a plus, because we have two minuses, and then we have B11 with a minus, and then we have B21 with a plus. And so once again, this cancels, this cancels, this cancels, this cancels, 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 cancels. The only thing that's left is this and that, which is A21, B11, and A22, B21, which is exactly what we have here. Okay, so that worked out. I screwed that up royally in the previous section. So I guess I'm going to be cocky, and I'm going to do the last one as well, the C22. So at this point, we've verified the first three of the claims, and now we're going to do the last one. So I have another opportunity to screw things up. Okay, so C22 is T2. T2 is T1 plus M4. T1 is M1 plus M2 plus M4. M1 is S2 times S6. M2 is A11 times B11. And M4 is S3 times S7. Now S2 is S1 minus A11, so this is A21 plus A22 minus A11, so this is S2, times S6 is B22 minus S5, which is B12 plus B11, because the two minuses. So we have that, and then finally we have to do S3. S3 is A11. How the hell do I get rid of this nonsense?
See?
No idea. Happened once before. Anyway, so S3 is A11. A21, and A7 is B22 minus B12. So A21, A22, and A11. So with B2 we have a plus. I'm sorry, we have a minus. So this is a plus, A21, A22, and minus A11. So that's B22, then B12. We invert those. This is plus and minus, and B11 we have minus plus plus. So that's that. Then we have B11 times B2 by B11, so this is a plus. And then we have A11 and A21 with B22. A11 with B22 is a plus, minus B12. What is that? A7, 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 where is this 7? Minus B12. Oops. What is that? M5 is, this is wrong. C2. This is a 5, not a 4. This is a 5, not a 4. This is 5. And so this is different. See, I screwed it up again. M5 is S1 times S5. S1 is A21 plus A22. And S5 is B12 minus B11. So we don't have that. We have, yeah. So A21 and A22. So we're looking at those two columns with B12 and minus and plus. And now we have that plus here. 1. So, no, hold it. S1 and S5. 2, 1, M2, M5. Let's do it again. Well, I'm running out of time. That's so let's B2, so this is a plus for A21, a plus for A22, and a minus for A11. Then and then we have A2, B12. So this is a plus, a minus, and a minus. And B11 is a minus and a plus and a plus. So then we have B11, A11, B11. So there's a plus. And then we have A21 and A22 with B12, 2 pluses and 2 minuses. Okay, so we got this, we got that, we got that. And so this cancels. This cancels, this cancels, this cancels, this cancels. What happened with this minus? Well, we're running out of time. You can verify it directly. We basically, the C22 is going to end up, if we do it, if I did it right, which I didn't, A21 times B12, which is A21 times B12. A2, 1B. So it should be something. I screwed up somewhere. And then the other one is A22 times B22. Well, yeah, I don't know. This should be, those two should be the results. And if you do it right, then you'll actually get it. Anyway, sorry about that. But you can verify it and you can determine how it's going to work. So, any questions? Homework 2, they were distributed. Homework 2 grades were long distributed. They were done before the exam. Monday night or Tuesday morning. Not for your session? Well, I'll find out. Let me find out. Any other questions? All right.
Well, Professor, I had a question. Will there be an assignment 3?
Well, if you didn't get a confirmation when you submitted your test, you should have submitted it again, because if you don't get the confirmation, it didn't happen. There's nothing I can do. Anything else? Don't email me. I can't do anything about that. You have to submit it again until it actually is confirmed. I am totally out of the loop in this case. That has to go to the 3320 at cs.uh.edu. Anything else? So I will try to find out what happened with the grades for the second section. All right. Talk to you on Wednesday. Bye-bye.